we're going to take this opportunity to duck into one of the specialist third year labs that Michael mentioned. So this is the Optics lab, and we have here Alexis Bishop, who oversees the third year labs. Do you want to tell us a little about this space?
Yes, so this is actually one of 3 specialist optics labs that we have in the third year. And so in this laboratory in front of me here, I have the optical tweezers experiment, which is where you use a fairly high-powered laser, which is focused at a very small spot, and you can use that to move microscopic objects around. And on this side over here, through the curtain, is a spatial filtering experiment. And interestingly, on this side, we have a single photon experiment. And so we put single photons through single or double slits, and we investigate whether or not a single photon can actually pass through 2 slits simultaneously. So an interesting quantum experiment there.
Yeah. Excellent. Thanks, Alexis.
No worries. Hi, everyone. My name's Alexis Bishop, and I'm one of the lecturers here at the School of Physics and Astronomy at Monash University. And what I want to talk to you today about is the optical tweezers experiment, which is an experiment that students do as part of their teaching studies. And optical tweezers is an interesting technique. It's been known for a long time that light has both momentum and energy, and it turns out that if you can focus light in a very small region, some interesting effects can occur. And so what we do in this experiment is take a moderately powerful laser beam of the order of 50 milliwatts and focus it to a spot which is about 50 times smaller than human hair. And at that focal point, the optical forces that are generated by the light are strong enough to actually be able to move objects around. And so in this experiment, we can pick up and move a very small, 1 micron sized or so, polystyrene spheres in water. And so we can pick them up, move them around, and do some experiments on them. And so the optical tweezers apparatus is in front of me, and we've built this ourselves at the university. And essentially what it is a conventional optical microscope, which is all these bits here. So it has an objective and instead of an eyepiece, we have a camera. And then we have some optics to introduce the laser beam into the microscope, so that the laser beam focuses at exactly the same place as the microscope focuses. So that allows you to see where the laser beam is hitting on your targets. And what we do is to do trapping, first of all, safety first, I'll put on my laser safety glasses. So here we're looking at a sample of the microscopic polystyrene beads that are in water, and they're trapped between a microscope slide and a cover slip. And you can see them bouncing around due to Brownian motion. And the beads are quite small. They're actually only 1.56 microns in diameter. And I'm looking just above the surface of the microscope slide, and I'm going to turn on the optical tweezers, and you can see that red dot. That's the optical tweezers beam reflecting off the bottom of reflecting off the microscope slide. And if I move the optical tweezers beam over one of the beads, it'll be drawn into it fairly quickly. In fact, you won't even see it, it'll go so fast. So it gets pulled in, and then I can drop the slide away from the bead, which you can see here. So you can see the bead still stays in focus, but everything else, the focus is changing, and that's because I'm I'm actually dropping the slide away from the bead. So all the other beads are going away from my trapped bead. And once it's trapped, I can move it around, there's no problem. And actually I can take it all the way up to the underside of the cover slip, which I'll do here. And then once that happens, the bead will be pushed out of the optical tweezers trap. And so very quickly it disappears all the way back down to the bottom of the slide. So I can pick it up again and move it around. And I can drop the bead by just turning off the optical tweezers trap and letting the bead float away and undergo Brownian motion. So if I turn the laser off, straight away the bead starts to wander off. If I turn the trap back on again, I actually managed to pull it back in. And so once again, you can put the bead wherever you want. move the bean up and down. And when you're finished, release it back to the wild.